in St. James, and I asked the Ford engineers for a simple animated demonstration of how fuel travels through the electronic fuel injection system of my car. Well, they took the time and produced their own version of a fantastic voyage through the system. Starting with a full tank of the right fuel, once you switch on the ignition, fuel begins traveling to the injectors and to your engine with pressure created by a fuel pump, or pumps depending on the vehicle. From the fuel pump, the fuel travels through a filter where any impurities are removed. Then it goes up a supply line. A pressure regulator supplies the fuel with a constant pressure as it travels across the injectors. The injectors mist the fuel into the engine, and then you're ready to do a few laps around town. And there's another fuel line that returns the fuel your engine didn't use back into your tank. Now that's a very basic explanation of how fuel travels through the electronic fuel injection system of a car. But basics alone aren't enough. You need more detailed information. So Ford Parts and Service Division has prepared this program to give you just that. Your instructor, Joe Connell, will be with you in a few seconds. He'll be your guide in the function and operation of electronic fuel injection. Well, I'll see you later. I've got a race to win.
Thank you, Lynn. Basically, electronic fuel injection is a more precise way of doing what a carburetor does. It delivers the correct air-fuel mixture to the engine at the correct time under all operating conditions. Fuel injection is more precise than carburation because it is controlled electronically rather than mechanically the way most carburetors are. In electronic fuel injection system, the amount and mixture of fuel are regulated by an electronic control assembly in response to signals from a variety of sensors. The electronic control assembly then controls the fuel injectors so that fuel is carefully metered and sprayed into the intake airstream. This precision control allows the engine to operate with an optimum air-fuel ratio throughout its entire RPM range and under all operating conditions. And because the air-fuel mixture in the combustion chamber burns more completely, it produces the lowest combinations of unburned hydrocarbons, carbon monoxide, and nitrogen oxides in the exhaust gases. Well, that's what electronic fuel injection does. But before we go on, here's an important tip. Electronic fuel-injected engines are more sensitive to dirt than carbureted engines. Dirt must not get to the injector side of the fuel line. The recommended gasoline must always be used to keep the fuel injectors clean. Remember that a fuel injector acts like the nozzle on a garden hose, only it's much smaller. If dirt or grit clogs the nozzle opening, fuel may not flow properly, causing the engine to run roughly, deliver less power, or even stall. Ford Motor Company uses three basic fuel delivery systems: high-pressure in-tank, low-pressure in-tank, and a combination of low-pressure in-tank and high-pressure in-line. In each system, an electric fuel pump supplies pressurized fuel to the fuel injectors. In the high-pressure in-tank system, the fuel pump supplies fuel at a pressure of 39 psi, even during extreme vehicle maneuvers and steep altitudes with low tank levels. The low-pressure in-tank system is similar in operation, except that its working pressure is limited to 14.5 psi. The low-pressure in-tank, high-pressure inline system has two fuel pumps. The low-pressure in-tank fuel pump sends fuel at 14.5 psi to an inline high-pressure fuel pump for delivery to the fuel injectors at 39 psi. All three systems are protected from excessive fuel line pressure. This is important because there are two fuel lines to consider. A supply line connects the fuel pump through a filter to the fuel charging assembly. The filter at this point is very important. It keeps dirt and grit from clogging the nozzle openings of the injectors. A return line returns any excess fuel not needed by the engine to the fuel tank. A pressure regulator controls and maintains a constant fuel pressure across the injectors. The regulator also traps fuel during engine shutdown, eliminating vapor formation in the fuel line, assuring instant restarts and initial idle speed. It also helps get that excess fuel into the return line and back into the tank. As I said before, fuel injection meters fuel into the intake airstream using one or more fuel injectors mounted either in an assembly, on top of the intake manifold, or in the intake manifold at each cylinder. As in a carbureted engine, the pressure difference between the inside and outside of the engine helps to determine the amount of fuel that's required for the engine to operate. In electronic fuel injection, sensors determine this difference as well as throttle position, engine coolant temperature, the temperature of air entering the engine, and the oxygen content of the exhaust gases to determine the amount of fuel required for an operating condition. The sensor inputs are monitored by an electronic controlled assembly, which controls the injector to provide the proper amount of fuel. Let's take a break and review this information. Ford Motor Company produces two different versions of electronic fuel injection: central fuel injection, CFI, and multi-point fuel injection, EFI. These systems are similar to one another, and each is controlled by an electronic control assembly, ECA. The main difference between the systems is the location of the injectors on the engine. In the CFI system, fuel injectors are built into a fuel charging assembly, which is mounted in a central location on the intake manifold. In the EFI system, the injectors are mounted in the intake manifold and spray fuel to the front of each intake valve. There are two types of CFI systems: high pressure and low pressure. In the high pressure system, fuel is metered by two fuel injectors. Each injector consists of a solenoid activated pintle and needle valve assembly. When a signal from the electronic control assembly activates the solenoid, the pintle is pulled upward off its seat and fuel sprays from the injector into the intake airstream. When the signal stops, the pintle moves back down to the seat and fuel stops spraying. The ECA controls the air-fuel ratio by pulsing the injector on and off. The low-pressure system uses only one fuel injector with a ball valve assembly instead of a pintle. The ball valve moves off its seat to allow fuel spray. Otherwise, operation of the low-pressure injector is very similar to high-pressure injector operation. The EFI systems use one injector for each cylinder. The manifold on which they are mounted is part of an assembly comprised of a throttle body, upper and lower intake manifolds, and fuel rail. The injectors and the fuel pressure regulator are attached to the fuel rail. The injectors have the same pintle and needle valve assembly as is used in the high-pressure CFI system. Injector operation is also the same as for high-pressure CFI. The fuel pressure regulators for both the CFI systems are bypass devices with fuel supply and return ports. As mentioned a few minutes ago, they are designed to help maintain a constant fuel pressure across the injectors. Inside the fuel pressure regulator is a spring-loaded diaphragm. The diaphragm opens the fuel return port when the required fuel pressure is exceeded, relieving some of the fuel pressure. The diaphragm closes the return port when fuel pressure is back to the correct level. In the high-pressure CFI system, the regulator is attached to the fuel charging assembly near the rear of the air horn surface and regulates the fuel pressure to 39 psi. In the low-pressure CFI system, the regulator is an integral part of the fuel charging assembly and regulates the pressure to 14.5 psi. The fuel pressure regulator for the EFI system also has fuel supply and return ports. The major difference, however, is that this regulator is controlled by intake manifold vacuum as well as fuel pressure. Under certain engine operating conditions, manifold vacuum helps the fuel pressure lift the diaphragm off the return port, reducing fuel pressure. Air intake for both systems is very much the same as on carbureted systems. When the throttle plate is opened, the outside air under normal atmospheric pressure is drawn through the air horn because the pressure in the intake manifold is lower than the outside pressure. On the high-pressure CFI system, two air horns are used which are very similar to those on a carburetor. The low-pressure CFI air intake is mounted on the side of the fuel charging assembly. Other than this, the air intake is the same as on the high-pressure system. Air intake on the EFI system is through a throttle body which is horizontally mounted. In both CFI and EFI systems, airflow is controlled by butterfly valves, actuated by a linkage and pedal cable arrangement operated by the driver, similar to the one used on carburetors. Now let's pause again to review the material we've just covered. The electronic engine control system, EEC, is a collection of electronic and electromechanical components which continuously monitor and control engine operation. The primary functions of the EEC system in fuel injection are to control the air-fuel mixture supplied to the engine and to control idle speed. The brain behind the EEC system is an electronic control assembly, ECA. It's a small microprocessor that receives input signals from a series of sensors. The sensors provide updated information relating to the engine operating conditions, including crankshaft position and engine RPM, intake air temperature and/or intake airflow, engine coolant temperature, exhaust gas oxygen content, EGR flow rate, throttle position, and barometric and/or manifold absolute pressure. The ECA then makes computations and comparisons with information held in memory and sends controlling output signals to the fuel injectors and other components to achieve the desired air-fuel ratio and idle speed. The ECA controls the air-fuel ratio on both EFI and CFI systems by varying the injector pulse width. That is, the amount of time the injector is open for each spray. A wide pulse width provides a rich air-fuel ratio. A narrow pulse width provides a lean air-fuel ratio. The ECA operates in two modes to control the air-fuel ratio: open loop control and closed loop control. In open loop control, the ECA ignores the exhaust gas oxygen level when it makes a change in the air-fuel ratio. Open loop control is used during necessary fuel enrichment situations, such as cold engine startup or wide open throttle. In closed loop control, however, the ECA gives priority to the exhaust gas oxygen level in determining the correct air-fuel ratio. The ECA controls the air-fuel mixture so as to produce a certain level of oxygen in the exhaust gases. In this way, the ECA monitors the results of its own output signals, forming a closed-loop control circuit. The ECA also controls idle speed, but it does the job differently for the EFI and CFI systems. For EFI systems, the ECA controls idle speed through the throttle air bypass solenoid valve. When the ECA energizes the solenoid, air flows through the valve, bypassing the throttle plate and increasing idle speed. When the ECA de-energizes the solenoid, there is no bypass airflow and the idle speed drops. For most CFI systems, the ECA controls idle speed through a motor. Acting on signals from the ECA, the idle speed control motor positions the throttle lever for the best idle speed for different engine operating conditions. As the motor plunger is extended, the idle speed increases. Well, now you've seen the basics of electronic fuel injection. Of course, Lynn's explanation was a lot simpler and faster, but we felt we should give you a few more details. Remember that all electronic fuel injection systems include three distinct operations: air intake, fuel delivery, and electronic control. We've given you the basics, but with some important specifics. There's a lot more to electronic fuel injection, particularly when it comes to diagnosing the system. So take the time and view part 2 of this program to learn some important diagnostic techniques. As for me, I'm going to take that fast lap and see if I can catch up to Lynn.